The Jordan Rift Valley contains the lowest land elevation on Earth. From the peaks of the Judean Mountains to the surface of the Dead Sea, the terrain drops 1,600 meters in vertical height. Standard meteorological models assume that evening winds in a deep valley are radiatively driven. As the sun sets, the mountain slopes cool, chilling the air immediately above them. That dense, cool air then slides down into the basin. However, the evening winds observed at the Dead Sea diverge from this pattern. Exactly at sunset, the valley is hit by a violent westerly wind that is aggressively hot, dry, and highly gusty. This is a Foehn wind. Tracing its origin requires analyzing the atmosphere as a heavy, dynamic fluid in motion, applying the same hydraulic principles that govern water rushing through a narrow channel. To isolate these events from standard nocturnal winds, researchers process years of meteorological observations through a probabilistic statistical mixture model. This algorithm identifies wind regimes based on their underlying physical properties. This scatter plot shows the potential temperature difference between the mountain crest and the valley floor against the resulting wind velocity. For a standard radiatively driven wind, a grouping appears here, a high temperature gradient of 7 to 13 Kelvin, resulting in a weak flow of just 1 to 3 meters per second. The Dead Sea Foehn events create a second distinct cluster. Here, the temperature gradient is negligible, sometimes even negative, yet the kinetic energy is massive, with wind velocities reaching up to 16 meters per second. Because there is no large temperature gradient between the crest and the valley floor, local slope cooling cannot physically generate the momentum required to move air at those speeds. Since the data confirms the wind is a high-kinetic, density-driven event, we must apply hydraulic flow theory to uncover its mechanical cause. The primary framework for analyzing these kinetics is reduced gravity shallow water theory. This model treats the atmosphere as a two-layer fluid system. A denser lower layer and a lighter upper layer are separated by a sharp boundary called a strong temperature inversion. Whether that lower layer moves past an obstacle is defined by the non-dimensional mountain height. If the calculated value is greater than 1, the heavy air mass lacks the energy to climb and stalls against the mountain. If the value is equal to or less than 1, the flow crests the peak. Once the air mass crests, its physical behavior is dictated by the Froude number. This metric calculates the competition between the horizontal inertia of the flowing air mass and the reduced gravitational acceleration, marked as G', which acts as a restoring force pulling the dense inversion layer downward. Tracking the Froude number as the fluid navigates the topography is the only mathematical way to predict if the air mass will gently roll down the leeward slope or accelerate into a violent windstorm. The sequence begins in the afternoon. Intense solar radiation bakes the deep basin, heating the valley's boundary layer. Simultaneously, a heavy, cool maritime air mass advects inland from the Mediterranean coast. The collision of the maritime air and the superheated valley air creates a severe horizontal temperature gradient across the mountain range. This sharp thermal divide physically shoves the denser maritime air mass toward the windward slopes of the Judean Mountains. As it climbs, the air behaves as a subcritical flow, moving slowly and physically thickening as it navigates the rising terrain. For the state of the fluid to change, it must reach a Froude number of exactly 1 precisely as it crosses the mountain crest. When it hits that critical threshold of the edge of the 1,600-meter drop, the fluid structure shears. It instantly stretches out, rapidly accelerating as it spills over the steep topographic cliff. The air mass is now in a supercritical state. To conserve momentum in this state, the layer must compress, becoming extremely shallow and aggressively fast as it plunges into the depression. This high-speed plunge continues until the flow hits the valley floor and collides with the slower ambient air, dropping its Froude number back below 1. The abrupt loss of its supercritical status forces the kinetic energy to dissipate, generating a chaotic atmospheric rotor known as a hydraulic jump. This Foehn wind represents a heavy fluid crossing a critical threshold, a supercritical plunge triggered by the sudden transition over a massive topographic drop. To verify this fluid model, meteorologists use Doppler wind lidars to scan the invisible atmospheric profile of the valley. This lidar visualization shows a Type 1 Foehn event. The data reveals a localized wind jet hugging the slope, maxing out at 5.5 meters per second at an altitude of 300 meters above the ground. Tracing the horizontal axis, the scan shows the high-velocity jet penetrating only a few kilometers past the base of the slope, before halting abruptly. This sudden dissipation happens because the supercritical plunge is met by opposing thermal upslope winds rising from the valley floor. The local thermal forces overpower the kinetic momentum. Type 1 events represent an interrupted fluid transition, where the physical plunge is successfully repelled by the valley's internal thermodynamics. A Type 2 Foehn event is the realization of a full, uninterrupted supercritical flow. This updated LiDAR scan shows a massive, high-velocity jet extending completely across the 15-kilometer horizontal axis. The fluid achieves extreme acceleration, sustaining speeds of 11 meters per second. Looking at the vertical axis, the boundary layer undergoes severe physical compression. As the fluid rushing down the slope and accelerates, its depth shrinks from 1,500 meters down to 350 meters. This compression aligns with the reduced gravity shallow water requirement. To maintain a supercritical state, the moving lane must become distinctly shallow and fast. Type 2 events provide the empirical proof that treating the atmosphere as a shallow fluid, reacting to an abrupt obstacle flawlessly predicts these violent downslope windstorms. The mechanics of the wind dictate the permanent microclimate of the valley below. During the 1,600-meter drop from the Judean crest, the plunging air mass undergoes intense adiabatic heating. The increase in atmospheric pressure compresses the descending air, raising its temperature by the time it hits the shoreline. This creates a climatological paradox. Because of this hot evening impact, the daily peak for lake water evaporation does not occur at solar noon, but shortly after sunset. The massive kinetic energy of the Foehn also acts on the valley air quality. A full Type 2 Foehn event aggressively flushes out the stagnant boundary layer. The high-speed rotor operates as an atmospheric vent, scrubbing daytime haze and aerosol accumulations out of the deep basin. Extreme topographic depressions act as powerful thermodynamic engines. They isolate boundary layers and convert pressure differences into high-velocity supercritical flows that dictate the local climate.